we had that first blank was the midline. And the midline is that line through the middle of the graph. It's a horizontal line. This right here is your midline. Okay. Your amplitude was the next blank. Amplitude is the distance from that midline to that highest point. Right? So that is our amplitude. And then the last blank was the period of the graph. And the period is how long it takes for the graph to start repeating. So if you just like start here, as you trace the graph right here would start repeating. So like that distance right there, that is your period of the graph. And if it is just a basic sine or cosine function, it is going to be 360 degrees or 2 pi, because that's one whole rotation around the circle. So obviously after you go past 360, you start just doing the same thing over and over again. So let's look at the types of problems you're going to see from this. So you will have some that will be just from graphs, okay? And from these graphs, you will be asked to find the midline, the amplitude, and the period of the graph, okay? And if your graph has numbers on the x-axis, like you see here, then you're going, particularly big numbers, you're going to assume, if they don't tell you otherwise, that you're in degrees. What would you assume you're in on example 2? Radians. So it really doesn't matter except for the period of the graph, which one you're going to use for that. The others do not matter. So if for number 1, I'm looking for the midline of the graph, that horizontal line that goes through the middle of this graph, where do you think that is going to be? 3. So if I like draw that in right here, it'd be right here. It's not labeled very well, but it's halfway between 2 and 4. So my midline, when you give the equation of a midline, you want the equation of the line. So you're going to have to say y equals 3. You wouldn't want to just say 3. Also, you can graph these on Desmos whenever we get to the ones where we're graphing. We can type in y equals 3. It'll graph that midline for us. Okay. All right. Okay. Amplitude is the distance from our midline to our highest point or to our lowest point. So looking at this graph, what does it look like our amplitude would be? Okay. 1, so it's not marked well on here. We could put like little tick marks here. So from the midline to that lowest point, how far is that? 2. Amplitude of this is 2. Or you could think from the midline up to the highest point, it's 2. Okay, so this graph has an amplitude of 2. The period of the graph is how long it takes for it to start repeating. So what I normally do for this is I just start like right there wherever it hits the x-axis. And I start to trace it. And as I trace this graph here, I'm going to go up. Have I started to repeat yet? No. Because I got to go up. I'll hit the x-axis, but I got to do the bottom part of the graph. Right here is where I start to repeat. Okay? The period is going to be this horizontal distance. How far is that if we look at our x-axis there? $180. So 180 would be the period for this. Okay? Questions? All right, so let's look at the second one. We're looking for the midline. That needs to go through the middle. What do you guys think for that? -2, right here. I'm going to draw it in. Okay, you want to look at how far it is from the highest and the lowest point. So 1, 2, 3, 4, 5 to the highest, and 1, 2, 3, 4, 5 to the lowest. So that looks like it works. So that midline is y equals -2. Now, I basically just answered the next question as I was counting there. What's the amplitude? It's 5. Okay. Okay. All right. Who thinks they might know what the period of this graph is? What do you think, Andrea? It's not 3 pi. It's close, but it is going to be 4 pi, because on this graph, if you start, it helps if you always start like right at the y-axis. So for this graph, we're not really looking for like when it hits the x-axis again. We're looking to when it gets back up to that maximum point, right? So as I trace this graph, it looks different until I get right here, right from maximum to maximum, and then it's going to be the same after that. And that is from 0 over to 4 pi. So the period for this graph would be 4 pi. Yes, test is going to be Wednesday. We will not have a separate quiz on this stuff. It'll just be on the test. Okay? Okay? We're looking at how long it takes this to repeat. So what I normally do is try to look from like that maximum point until I get back up to the other maximum point. And I'm thinking about how far apart these two are horizontally, which you need to look at your x-axis for that. So that's from here over to here, which is 4 pi. Okay, questions? Okay, let's move on. All right, now there are ways to figure this out from the equation rather than from the graph. Okay, now you certainly can use the graph on pretty much everything. You can use the graph on pretty much everything because you can type all of these into Desmos. So you can always use the graph to help you, but a lot of students find it a little bit easier just to look at the equation. This stuff can go on a note card if you would like. So if you want to add this stuff to your note card as we go, you can. The only thing that cannot be on your note card is the unit circle. Unit circle cannot go on your note card. I will give you blank ones. I'm not going to have you like fill it out as part of the test. But what you're probably going to see is like you have to find sine of 30. And so you may want to fill out the whole thing, or you may just want to do the parts you need. Okay? All right. Okay. So if you think back to when we were doing some shifting of graphs, we would move them up, down, left, right, flip them upside down, those sort of things. We talked about how we could shift different graphs for this. What did it do if we added a number to the end of the graph? What? Moved it up, or if we subtracted it, move it down, right? So think about these graphs, these curved graphs. If I take a number and add it to the end, it's going to move it up or down. That midline is usually at the x-axis, but if we shift it, the graph up or down, that midline goes with it, right? So the midline is going to be y equals c, whatever that number is that's added or subtracted to the end. Okay. We did not really do a lot of, well, we did a little bit, I think, of like stretching a graph out or shrinking it, like making it taller and skinnier or shorter or fatter. Which number, the A, B, or C affected that? What number? It was the A. So amplitude is going to be stretching it out or shrinking it down, right? Because if we stretch it out, it makes the amplitude higher. If we shrink it down, it makes it lower. So the amplitude is really easy to find from the graph. It is just whatever it is. Actually, it's absolute value of A. So you might want to put yourself a note over here. Amplitude is always positive. So that means even if you have an equation that has a negative 5 out front, the amplitude would just be positive 5. Okay, amplitude is always positive. That negative, what it's doing is it's flipping the graph. So those are separate pieces. Okay. Now, I'm mostly going to ask you to find the period of a graph whenever this is in radians, because I think that's what they're going to ask you more. However, I looked through the standards for the class, and it does say you're supposed to be able to do this with degrees and radians, so I'm putting them both in here. I know problems I have seen are typically more radians than they are degrees. So the period of a function is going to be, if you're in degrees, it's going to be 360 divided by b. If you're in radians, it is going to be 2 pi divided by b. Okay, b is this number here beside of your x. Okay? All right. Okay. Questions? Okay. So, let's look at doing some of these. We're going to do them from the equation and from the graph. We're going to look at Desmos for these as well. So let me pull up Desmos here also. Where'd that go? Okay, so if I type in, and you guys type this in on your computers as well. Go ahead and get out your computers. I want you guys to see it. Okay, if you don't have it out, get those out. Y equals 4 sine of 3x minus 1. All right. So, go ahead and type in this first one into Desmos. And I'm going to show you, we can do these from either the graph or the equation. Just type in SIN. Have you finished typing the rest of it in? Have you got parentheses? Make sure you got an X. It is going to depend on if you are in degrees or radians, probably. If you're in degrees, it's going to look like this. All right. Let's do radians first, and then we'll go back and look at it in degrees. Okay. I think you're going to see radians most often on this, although there's a chance they use degrees. So, I definitely think that midline and amplitude are sometimes, they're not that terrible to find from either one. But the midline of this graph, we could look and see where we think it is. Where does it look like it is at? Okay. I can test that by typing in y equals -1. Does that look correct? You want it to be halfway between. You want it to be in the middle. But, guys, quiet. But, notice that our formula said that the midline is always going to be this last number right here. And it is. It's -1, right? So you can just pull this off from the equation. So, for example, 4, what's the midline going to be? Y equals -40. So we can do it without even graphing it, right? But it may be helpful to graph it if you've maybe forgotten what it is. All right? Amplitude. So if I'm looking over here at my graph, how far is it from that midline up to the top? Let me zoom in a little bit here. You're going from the blue line to the highest point. Blue line to the highest point. 1, 2, 3, 4. Okay? Oh, sorry. Okay? We get 4. Notice, that was this number right here. That number is always your amplitude. So if I go over and look at example 4, example 4 is a little tricky.
0. None.
It's not 0.
None.
If there's not a number there, what number is it?
1.
1. So the amplitude would be 1 for that. So you can graph it for sure, or you can just use that number, right? They're both there. All right, so for the period of the graph, first of all, if I'm in radians, this is kind of hard to see right here. I can sort of look. Right here is my y-intercept. And if I want to look at this graph, I go up, back down, negative part. Right here, I start to repeat. Right, so if I'm looking right here, I'm going up, back down, and then right here I start to repeat. But is it very easy to figure out what I've got right here? No. So here's a trick. Everybody go up to the wrench on your graph. Okay? On your x-axis, right here it's going to say step. That step is what it's counting by. And we don't really want to see 0, 1, 2, 3, 4, 5, because whenever we're dealing with radians, like if you think about the unit circle that you just did, radians were hardly ever whole numbers, right? It was really only whenever you were at 0 that you got a whole number. The rest of the time it was like pi over 2, pi over 3, 5 pi over 4, that sort of stuff, right? So a good thing to use is maybe pi over 4. If you just type the letters pi, it'll put a pi and the division key 4 and hit enter and then go back to your graph. This still may not help us all that much. Because if I look at this graph, I'm looking from here to here, and I know it's less than pi, because pi is right here, but I still can't really tell what it is, correct? So this is where it becomes very helpful to use the formula that I gave you on the last slide. Because sometimes the period of the graph is really difficult to find by looking at the graph. Sometimes it's not. Sometimes it's very clearly marked. It's pi, or it's 2 pi, or it's 4 pi. And if I'm asking you to do the problem strictly from a graph without the equation, I will make sure that it is one where you can see it on the graph. But this one we can't see on the graph. That's why I've given you the equation. So, we're in radians right now. For our formula, the formula for the period of the function is 2 pi divided by, actually let me use a different color, let me use this black right here, 2 pi divided by the number that you're multiplying your x by. Okay, so 2 pi divided by 3. Now, if you go over here, let's see if it'll work, it may not. If you go over here and make your step 2 pi over 3, it might label it. It does. But see, I had to know what it was to know what to type in there first. So and I can see that looks like the correct length. So knowing that formula is going to be really important. You can have that written on your note card, right? The only thing you can't have on your note card is your unit circle. It's from the last slide, the stuff we filled in on the last slide. Okay. Now, we can also do this in degrees. I think you're most often going to see this in radians. If we do this in degrees, instead of having 2 pi, what is a full rotation? It's 360. So we do 360 divided by 3, and that would give us 120 degrees right there. Let me show you this from the graph. Here. Okay, so whenever we first graphed this, some of us were not getting a curve. You were getting a line. It looked like this. It is because you were in degree mode, right? So if you're in degree mode, you need to have a full, at least 360 degrees, right? So if you go up here to your wrench, your x-axis only goes to like 8.859, or mine does any right now. So if you make your x-axis like negative 360 to positive 360, you'll be able to see this. And let me go there, and I'm going to tell that step, let's just go up by 1. Let's not do pi's anymore. And so you can see this on your graph. And you can see right here, this point right here is 120. So you know what the value is there. Degrees are a little easier to find the period from the graph. Okay, questions? All right, I'm going to go back to radians. Look what happens if I go back to radians. It turns into a block. Why is that? I'm going from 0 to 360 right now because I was in degrees, right? So 2 pi is like 6.28, right? 6.28 is one full rotation. Right now I'm going from 0 to 360. This is tons of rotations. So watch what happens if I make these numbers smaller. If I make that 0, if I make this, actually you can just type in 2 pi, then you'll start to see the curve again. It was just, it had lots, it was so many like zigzags in between there squished in that it looked just solid for that. Okay, so we already found midline and amplitude for example 4, but let's type it in. F of x equals sine of, use an x instead of a theta for that. All right, I can't see it. Why can I not see it? Okay, let's go to radians. Actually, I am in radians. Definitely, let's get rid of this too. Definitely, I can't see it because where's my midline? Negative 40. And I am at 0 right now. So I need to go over here to my y-axis and make that lowest number like negative 50 or something like that. Okay, I can see it a little better now, but I think I need like more. Let's go from like negative 20 to positive 20 over here. Okay, now I can at least see I've got a curve, right? So I've already found the amplitude is 1 and the midline is negative 40. So if I type in y equals negative 40, it'll graph that there for me. And so I'm looking at how long it takes this to start repeating. That happens right here. Oh, it labels it 6 pi. I didn't realize it would do that. That is actually very helpful. Let me go back to the last problem. Well, let's finish this one. So if you graph your midline, I did not realize it would do this. This is very helpful, actually, because if you go to that point right there where this starts to repeat, it's labeled 6 pi for you. So your period for this graph would be 6 pi. Now, if you do this using the formula, there is something that you need to know. Theta divided by 3, it's like there's a 1 right there with that theta. So this is the same thing as 1/3 times theta. So if we want to use the formula for this, we're going to be doing 2 pi over 1/3. And dividing fractions is easy as pie. Flip the second and multiply, and that's where we get our 6 pi. So that's a little bit tricky because of that fraction there. In degrees, we would be doing 360 divided by 1/3. And dividing fractions is easy as pie. Flip the second and multiply. 6 right there. And that is going to be 3 times 360, which is 1080. Yep. So we'll get 1080. I think you're going to see it done in radians more often, but I don't know about these. All right. The next one. Let's try to do this whole thing without graphing before we look at it on the graph. So, Katie, what would the midline for example 5 be? It's a little bit tricky. It's a little tricky. It's 0. Because there is nothing on the end, and it's not going to be 1 this time, because you can't add 1 and it stay the same, right? I could put a +0 over here, though, and it wouldn't change anything. So my midline for this is going to be y equals 0. It comes from the fact that you got nothing there on the end. Okay? Drew, what's the amplitude? 10. Okay? Now, our period is a little bit more difficult to find. Let's deal with radians first. So, the number that I have multiplied by my variable, your x or your theta are the ones I'm normally going to use for your variable. So, that number is complicated here. It's 5 pi over 4. So, if I have, let's do this actually, right here, 5 pi over 4. So, my formula says 2 pi divided by that number multiplied by your variable. So that's 5 pi over 4. Dividing fractions is easy as pi. Flip the second and multiply. So I got 2 pi times 4 over 5 pi. Now, that 2 pi, I'm going to put it over 1. What could happen with those pi's? Cancel. The pi here cancels with the pi here. And I will get 8 over 5. So 8/5 is going to be my answer in radians. If I'm doing this in degrees, it is going to be 360 divided by 5 pi over 4, which is going to be 360 times 5 pi over 4. I would just multiply this without the pi is probably how you're going to see it. You're probably not going to see this one with degrees, honestly. If I do 360 times 5 and then 1800 divided by 4, I'm going to get 450 pi. I really don't think you're going to see that. It's going to be in radians probably. So it would be 450 pi. Okay. Let's look at the graph to check. So for the radians, every time you do 2 pi divided by whatever number is being multiplied by your variable, which that theta right there, that's your variable. So it's all this 5 pi over 4 stuff is your number. So you're doing 2 pi divided by 5 pi over 4. And dividing fractions is easy as pi. So you're going to flip the second and multiply. The bottom fraction is your second. So you got 2 pi times 4 over 5 pi. We flip this fraction right here upside down. If there is a pi in your fraction, it usually does. Yes. Like, for example, 4, it did not because we just had a 1/3. So it was the same thing with fractions, but there was no pi to cancel out for that. All right, so if we graph this, the graph can always help you too. I got h of x equals 10 sine of 5 pi over 4 times, use an x instead of theta. So there's my graph. let's go to, we're in radians. Let's just hit the house button here. Okay, that's, all right, if I type in y equals 0, that'll put my midline in. And then it does show you, like if you're, I'm going to zoom in. Well, I don't really want to zoom in. Well, if I trace this, if I go up, back down, and then back to here, right there, guys, there's a lot of talking. Okay. There, right here, I got 1.6. What is 8/5? If I give it a decimal, it is 1.6. That is my period for my graph, so I know I've done this correctly. And change to degrees if you want. Okay. All right, let's do number 6. Wade, what's the midline of number 6 going to be? Good. We'll have y equals 3 for that. Correct. Wonderful. So midline is y equals 3. Amplitude is positive 5 because amplitude is always positive. That negative is going to flip the graph upside down. It does not mean the amplitude is negative. All right. For the period of this function, we got to take that number that's multiplied by the x. What number is multiplied by x? 5's on the outside. It's your amplitude. 3 is on the end. All right, so this does not have parentheses, so if there are no parentheses, the parentheses just go around that x. And so we just have a 1 right there. So you don't even have to write this down. You're doing 2 pi divided by 1, which is just 2 pi, right? And then for degrees, you'd be doing 360 divided by 1, which is just 360 for that. Okay. So on these, you're welcome to use the graph. You know, you can graph this. Y equals negative 5 cosine x plus 3. If we graph it and you graph y equals 3, you can see that's your midline. You can count 1, 2, 3, 4, 5 is your amplitude. The period is a little bit more difficult to do right here because you're going to this like minimum point, but it still tells you it's 2 pi right there. I always start at the y-axis and then just look at when it starts to repeat. That happens right there at 2 pi. So that would be your period for the graph. Okay, questions? All right, let's look at some application for this. So we're just going to kind of scratch the surface on application for these. And for this one for sure, this is done in radians. So you want to make sure you're in radians on your graph. And I'm going to type in y equals 2 cosine of 2 pi over 12 times x, close my parentheses, plus 12. And so that gives me a pretty good graph right there. And it tells us this function gives the number of hours of daylight X days after the summer solstice. Okay, so what is the summer solstice?
The sun.
It's not just, it does involve the sun. It is the longest day of the year. Okay, so and you can see that makes sense because you've got the longest day of the year. So if we want to know the period of this function, right, we want to look at this graph. You can do it from the graph or you can do it from the equation. All right, from the graph, we start right here at a maximum point. We're going to start repeating when we get back up to that maximum point again. Right? How far was that? From 0, 14 to So 12, 14 is 12. Okay? And, oh, I'm sorry. This is bad. I've got a mistake on this question. Days right there, it shouldn't say days. It should say months. Because how often would you expect this pattern to repeat? It's the number of hours of daylight. So, okay, so to answer that question, number of hours of daylight, is it always the same? Okay? We just said on the summer solstice, longest day of the year, right? And then after summer solstice, what happens to the number of hours of daylight? Decreases. Then it would increase again till it gets to the summer solstice again. How long does that take? 365 days. But the period of this is 12. That's why I'm telling you it's a bad problem. That should not say days. It should say months, because this is counted in months. It's 12 months would be a year, right? So the period of this function is 12. It says, what is the maximum hours of daylight this town sees? So that's pretty easy to find from the graph, right? It's going to put all of your maximums here. You're just going to go to any of those maximums. What's the answer, 12 or 14? It's the y coordinate. It's your 14. What's the minimum? Nope. Go to the minimum. Just go to the minimum. What is it? Not 6. 10. It's your y coordinate. Okay? Now, let's think about this. Let's think about this from the equation. What's the midline of this? What's the midline of this equation? Y equals 12. Right? That's the midline. So the maximum is going to be the midline plus the amplitude. Right? What's the amplitude for this one? Okay, so let's say if I don't have the graph, I've only got the equation. My midline is 12. And my amplitude is 2. So for this, if I don't have the graph, I could just do 12 plus 2, which gives me the 14. Right? Because it's the distance from, I'm going from the midline up to that highest point. If I'm doing the minimum, how can I do that without the graph? Subtract 12 midline minus the amplitude. That gives you your minimum. That gives you 10. Right? I don't care which way you do that. We were just having a little trouble with deciding the x or the y coordinate there, so this may help some. All right, what is the average amount of daylight that this town sees in a day? Nope. The only places that see 24 hours of daylight are like Alaska, where it doesn't get dark. 4 would be a very small amount of hours of daylight.
12.
Okay? Why are you saying 12? 14 and 10, that's your midline. Your midline is your average here, so it is 12.
Oh, that makes sense.
Yep, your midline is your average here. Okay, questions? All right, let's go to our next one. Okay, now, you guys need to listen to this, because whether or not you care about this math at all, this is fascinating. So, a couple years ago, I read a book called, I think it was called The Devil in the White City. It is a fascinating book. It's a little dark. It is about the World Fair in 1983. So, in 1983, in the U.S., we held the World Fair in Chicago. And so, the World Fair in Chicago was a huge event, and 4 years prior, they had held the World Fair in Paris. And at the World Fair, each country that hosted the World Fair tried to build like a centerpiece or do something magnificent that had not been done before. So, in Paris, does anybody know what they built at the World Fair in Paris for you?
Eiffel Tower.
Statue of Liberty is in the U.S. Although it wasn't built around the same time. Eiffel Tower. Eiffel Tower was their centerpiece. Okay? The U.S., for their World Fair, was wanting to build something that would also be the centerpiece of this. And you're looking at your picture, and you're like, that's a Ferris wheel. That's not impressive. But here's what you need to know about Ferris wheels. Okay? This is I put 1983. It's not 1983. It's 1893. Let me fix that. Ooh. Fix that on your notes, or this is not impressive. That's not very long ago. Let's see. 1893. Let's fix that. Make this accurate. Little typo there. Okay, so let's talk about 1893, because I think this was crazy. It covered it a lot in this book that I read. So in 1893, okay, we're talking about a time where electric lights are new. The majority of people do not have electric lights in their home. A lot of people, though, at the World Fair, everything had electric lights, and a lot of people went to the fair just to see electric lights because they had not seen them before. Okay? At this time, I put this on here because this is important. At this time, the tallest building we had built was 348 feet tall, which is, I mean, it's a pretty tall building, but, you know, skyscrapers these days are, you know, well over 1,000 feet tall. So the tallest buildings we had even built were 304. The very tallest building in the world was 348 feet tall. We did not know how to build things that were very tall. So the engineer, I can't remember his first name, but his last name was definitely Ferris, that decided to do this. His last name was Ferris. Mr. Ferris was 33 years old, and he decided that he was going to build a Ferris wheel. Okay? This had never been made before. There were some like wooden structures that were a little bit like they were wheels, but they were much smaller and they did not operate the same. So, Mr. Ferris designed a Ferris wheel for the World Fair. And this is the first Ferris wheel we've ever made. Ever. And the first Ferris wheel that he made was 250 feet tall. Remember, the highest building is 348 feet tall. This Ferris wheel, each one of these cars on this Ferris wheel held 60 people each. They were like train cars. This is not just like your little Ferris wheel that you see. There were 60 people apiece in each one of these. So this Ferris wheel held 2,160 people whenever it was fully loaded. 2,000 people on this Ferris wheel at the time. We have never made one of these. We don't even know if it's going to work. There's a lot of people saying that it was too fragile and it was just going to like collapse as soon as you got it fully loaded. Okay? When they built this, it didn't have any of the cars on it. The workers that were building this, several of them, I'm sure all young males, whenever they rotated it for the first time, not even with cars on it, several of the workers like just jumped on and grabbed onto this and rode it around 250 feet in the air without being secured to this at all. Yeah. It took 9 minutes for it to go all the way around without stop. So it took longer than that for it to load and unload. Okay? It was powered by steam engines because remember, we can just barely run electric lights at this point. It cost you 50 cents for a 20-minute ride, but that was just around twice for this. Okay? So, I was fascinated by the fact that the very first one that we ever made, we made it gigantic. This could have been a giant death trap that killed 2,000 people at one time. Thankfully, it was not, and it worked. I feel like we would never build something like that these days without a lot of testing, but they did, and it was pretty fascinating. The other half of that book is about a serial killer that killed multiple women at the World Fair in Chicago in 1893, and he got away with it because he had like built basically a crematorium in his house, like in his apartment complex. So he was like cremating these women. Yeah, it was bad. It is about the World Fair. It's about the serial killer, but like at the same time, it tells you a lot about the World Fair. So there's a lot of it about the Ferris wheel in here because it's pretty fascinating too. But the main focus is the serial killer. It's called the Devil in the White City. I can't remember his name. I think it was Eric Carle. No, not Eric Carle. That's like Eric Carle is the little ladybug book. I can't remember who wrote it. It's Eric something. Larson.
So is that a famous serial killer, or is it just like a...
Yeah, it was pretty. I mean, he doesn't. I don't think he had like a nickname, but yes. So anyway, it was a very interesting book. It's a little dark, so I wouldn't recommend it if you don't like things that are dark. But it was interesting. Anyway, let's continue on because we've got to.
Just a question.
Yes.
I swear the Statue of Liberty was built in Paris or France or something.
Yeah,
It was a gift.
But it was built there, wasn't it?
I don't think they shipped that maybe over here. I don't know. It was definitely a gift. I don't know if it was built there or here. But
Hey, look.
I'm thinking that it had to, even if they did build it there, it had to be assembled here. It could not have been shipped over in one piece and just put up. All right. Okay. All right, so let's look at this because I think they're, or at least they say they're going to give you some of these problems, and it could be something you see. So we're going to write an equation for your height as you go around this giant Ferris wheel. Okay, so this tower right here in the middle is 140 feet tall. So like that center of the center of the wheel is 140 feet off the ground. Guys, quiet. Okay. Center of the wheel is 140 feet off of the ground. Now, those cars don't go all the way to the ground. Think about just riding a Ferris wheel at the fair or somewhere. Usually whenever you ride a Ferris wheel, you've got to walk up on a platform to get up onto the Ferris wheel, right? Because we don't want these cars skimming the ground each time they go around, right? So, for this, the midline of this should be 140 feet, right? That's the middle of this graph. So, over here, we know that midline needs to be y equals 140. Okay, let's go over here. Let's graph y equals 140, and let's get our window where we can see it. I'm going to hit the wrench right here, and I need my y-axis to go up to well over 140 because that's our midline. So let's do like 300. That might be enough. Okay. All right. What would the amplitude be here? It's not going to be 250, but it comes from 250.
No, 110.
Where'd you get 110?
I subtracted 250 from 140.
No. That would make sense, Drew, if both of these lines went all the way to the ground. But they do not. This line right here is a certain amount off the ground. Okay. I don't think it's 20. So the midline from the highest point to the lowest point of this, your diameter is 250. The amplitude is just from the middle to the lowest point, right? So if we take 250 and divide it by 2, we're going to get 125. That should be our amplitude. Okay, now the period of this graph is more difficult, or the period of this graph is not difficult to find. They told you what it was. How long does it take for this to start to repeat? 9 minutes, right? Okay, now the equation, part of it is really easy to come up with, okay? Because midline and amplitude are just in your equation. So we're going to have y equals, actually I'm going to show you something right here. Whenever you get on the, when you get on the Ferris wheel, are you getting on at the top of the Ferris wheel or the bottom of the Ferris wheel? Bottom, right? So sine and cosine of x, let me go ahead and put in y equals 140, no, wrong, 125 cosine x plus 140. Okay, the period is not correct on this yet, but this graph looks like you get on the, this graph looks like you get on the Ferris wheel at the top. We don't get on the Ferris wheel at the top. We get on the bottom. So watch what happens if I put a negative right here. It flips it, and now you get on the Ferris wheel at the bottom. All right, so that's why I'm putting the negative here. It'll be multiple choice. You won't have to make these entirely from scratch. So I will, have those answers there. So we're going to do negative 125 is our amplitude. We got cosine. I'm going to put x right here. I'm going to leave a little space because I need something else to go there. And then plus 140. So this gets us almost there. And probably you're going to be like, this is going to be a multiple choice situation. And you'll be able to rule out a couple answers because of the midline or the amplitude not being correct. So the period is what makes it most difficult to find. I want the period of this graph to be 9. Right now, if you look from the lowest point back to the next lowest point is 2 pi. 2 pi is like 6.28. That's not 9. So I want it to be 9. I could try to put just like, I got parentheses here. I could just try to put 9 right there. Oh, wait, not 9 minus x, 9x. That definitely did not do it, right? That messed up our graph bad. So that does not work. All right, so to find the period, and you'll have multiple choice, so you won't have to do this a lot. This right here, I don't know what that is. To find the period, I have to do 2 pi divided by that number in front of this, right? And I need that to equal 9. Okay, so to find this by hand, I would multiply both sides by b. So 2 pi equals 9b. And I would have to divide by 9. So what goes there, where that b is at, is 2 pi over 9. Now, you're going to have these are going to be multiple choice. So you won't have to write that by hand. You'll just have to match it. So if you have an answer choice with 2 pi over 9 right there, you can see if you go from your lowest point to your next lowest point, you have a period of 9. So you would know that would be the correct answer right there. Okay, so this graph would tell you how high you are on the Ferris wheel. So like if I want to know, let me call this f of x. Okay, if I want to know how high I am on the Ferris wheel after 3 minutes, f of 3 is going to give me 202.5. Right? If you want to know how long it takes to get to the maximum, you could just look here. You got 4.5. You should kind of know that because it's half of the time. There, half the time going up, half the time going down. If you want to know when you're at the midline, you're at 2.25 minutes. So there's several things they could ask you about this. Here. Also interesting, in that book, it said that, this is the late 1800s, They weren't really big on safety. I've already highlighted. So the cars didn't lock. They didn't have they had doors that shut, and they were glassed in so that you wouldn't fall out. But they didn't lock. So, and you got to also keep in mind, people had never been this high in the air before, because like at your maximum is like 260 feet in the air, right? So people had never been anywhere close to this high in the air before. Most people have never been in a building this high. So, and this is kind of like you know how Ferris wheels are a little shaky anyway. That there was one incident where one person like went crazy and was trying to jump out because they like lost their mind. And they kept like banging, they were trying to get out, and all the other people, because you got to remember there's 60 people on here, had to like tackle this man and hold him down for the rest of the ride because he was going to jump out of the, it had glass. You wouldn't fall out easily, but the door did not lock in any way. Yeah. All right, last one. This is our last one, right? Okay. All right. Okay. All right. We're looking at tides this time. Low tide was a depth of 1.8. High tide was at 3.6. Actually, let's still need this. Okay. All right. So I'm gonna type in y equals 1.8. Y equals 1.6. I'm gonna hit the house. Guys, quiet. I'm sorry, that should be a 3.6. Okay. All right, so here's I want my graph to go between these two. I've got y equals sine of x is right here. What should the midline be? Where's it going to be? It's not going to be 0. Right now it's at 0. I want high and low to be here. It's got to be halfway between 3.6 and 1.8, right? So 3.6 might be 2.5. Let's try it. Let's put plus 2.5. Nope, not enough. If we do 1.8, 3.6 plus 1.8 divided by 2, we're going to get 2.7. Okay? All right. Amplitude. What's the amplitude going to be? It's too much right now. If we take our highest minus our lowest, 3.6 minus 1.8, that's 5.4 feet that we need. I added, sorry, that's not. 3.6 minus 1.8. We get 1.8. If we divide that by 2, we've got 0.9 there. So this equation right here is going to be y equals, actually, we know we're going to have a 0.9. Actually, let's see. Let's do the negative and let's do cosine again. Make that negative cosine so we start at low tide. It'll be multiple choice, so you won't have to worry about that part. All right. Let's put this right here. And then we've got plus 2.7 here. All right. Right now, the period of this graph is 2 pi. If it took 6 hours to go from low tide to high tide, how long will it take you to make a full rotation back to low tide again? 12, right? So we want this to be 12. So, if we do 2 pi divided by b equals 12, that's 2 pi equals 12b divided by 12. We're going to get pi over 6. So pi over, and it'll be multiple choice, so don't worry too much about how to figure that out. It'll be multiple choice when you see it. So if I do pi over over 6 times x right here. Now I have my graph like it needs to be right here. If I want to know the depth of the water after 21 hours, I just need to plug in 21. So I do negative 0.9 cosine pi over 6 times 21 plus 2.7. And I would get 2.7. All right, so your assignment for tonight. All right, assignment for tonight is on Desmos Classroom. Let me pull it up real quick while you pack up. All right, it's 7.4. Do the first 7 slides, okay? First 7 slides.